All right, so to go over some implicit differentiation, tried to give you a little bit of help in understanding that we need to be looking out for a product rule when applicable. But to get started, it says we have secant of xy is equal to x, and we are looking to find dy dx. So I'm going to start just by rewriting the problem. And then in order to find dy dx, I need to take the derivative with respect to x. So the derivative of secant is going to be secant, leave the inside alone, tangent, leave the inside alone, times the derivative of the inside. Well, the derivative of the inside needs a product rule. So first times derivative of the second plus the second times derivative of the first. All of that will be equal to the derivative of x with respect to y, with respect to x, which is just 1. All right, well, I'm supposed to isolate dy dx. So I'm going to start by dividing both sides by this secant xy, tangent xy. So we're left with x dy dx, x dy dx, plus y is equal to 1 over secant xy times tangent xy. And if we remember from trig identities, that means x dy dx plus y is equal to cosine of xy times cotangent of xy. So finally, to isolate that dy dx that I was looking for, I'm going to subtract y from both sides and divide both sides by x, which will end up being answer choice D for this question. Okay, next one. If x plus 2y times dy dx is equal to 2x minus y, what is the value of the second derivative at the point 3, 0? So we're looking for a final answer that's a value. Well, before I can take the second derivative, I'm going to choose to isolate the first derivative. This doesn't have to be your first move. You could do a product rule on the left side to get started, but I think this makes things a little bit more clear. So I'm going to take the derivative with respect to x, because then on the left side, I get d squared y. On the bottom, I get dx times itself, which is dx squared. Then I'm going to need a quotient rule. So low d high minus high d low. Notice that every time I take the derivative of y, I use a dy dx all over low squared. Now that I've taken the second derivative, it is safe for me to plug in the point 3, 0. So everywhere I see an x, I'm going to replace it with a 3. So this will become a 6. Oops, there should be a minus there. 1 plus. There was a 2 there. Sorry, I'm just setting myself up. This will be 3 plus 2. All right. Everywhere I see y, I'm going to replace that with a 0. Oops, there should have been a 2 still there. Keep up, Schwartz, keep up. This one is a 0. That all looks good. This is a 0. And now I'm stuck because I still have some places where I need this dy dx. Well, luckily for me, dy dx is right here. And I can plug in 3 and 0. And I'm left with 6 divided by 3, which is 2. So everywhere I see a dy dx, I'm going to replace with a 2. Now I can just do some arithmetic to clean up my answer. So I'm going to have 3 times 0, which will be gone, minus 6 times 5 all over 3 squared, which is negative 30 divided by 9, or negative 10 thirds. Answer choice A. So again, once you've taken the derivative, or in this case, the second derivative, then it's safe to start subbing in your values, right? We're ready to evaluate the item that we found. The biggest thing here is that you already know x, you already know y. You just have to do a little bit more math to find that dy dx value. For response, consider the closed curve. Here's our original function. Says that we can show dy dx is equal to this expression. Find the derivative and find the values of a, b, and c. So I'm going to start, again, just by rewriting my function, not function, rewriting my relation. This is a closed curve, not a function. I'm going to take the derivative with respect to x. So the derivative of y cubed with respect to x is going to be 3y squared dy dx minus, to take the derivative of xy, I once again need the product rule. So first times the derivative of the second plus the second times the derivative of the first. Finally then, that's all going to be equal to the derivative of 2, which is 0. The reason why it's important to keep parentheses is that you want to make sure this negative sign distributes. Maybe you did that kind of naturally in your product rule because you decided to say it was a product between negative x and y, and that's totally fine. I don't care how you got there, but you do need to have a minus y on that left side. So then from here, I'm looking to isolate my dy dx. So anything that has dy dx stays on one side, anything that doesn't gets kicked to the other. And then I factor out my dy dx. So this is a 3y squared minus x, add that y to the other side. Finally, to get dy dx by itself, I'm going to take y divided by 3y squared minus x, which means that my a value is 1, my b value is 3, and my c value is -1. Now, if you chose to move your dy dx's to the other side, that's fine. You may have ended up with -y over -3y squared plus x, and that's okay. You would have some different numbers than I do, but I still looked for that in terms of giving you credit, because those are mathematically equivalent statements. Next thing then, using your work from part A. Well, what was all my hard work in part A? It was finding that the derivative is equal to y over 3y squared minus x. I'm supposed to write the equation of a tangent line. As soon as you see this, you want to set up point-slope form, which means that I need a point and I need a slope. Well, my point, I know the y value is supposed to be 1, so I can put a 1 there. How do I get an x value? Well, anytime we need the missing coordinates on our function, we just go back, our relation in this case, we just go back to our original curve. So I'm going to plug in 1 cubed minus x times 1 is equal to 2. 1 minus x is equal to 2, which means that x is equal to -1. Okay. Last thing I need then is the slope. Specifically, I need the slope at this point. Well, here's my general slope. So how do I find the slope at this point? I'm going to sub in a -1 for x, a 1 for y, and a 1 for y, and I end up with 1 over 3 times 1 squared minus a -1 for a slope of 1/4. So again, it's not enough to just find the overall slope, the derivative. We need to know the slope specifically when y is equal to 1 and x is equal to -1. Now, had you made a misstep in part A, but used your misstep correctly in part B, you should receive some partial credit because we do try to read with you and help you navigate through each problem. The last part, determine if the implicitly defined curve, which was y cubed minus xy equals 2, has any horizontal tangents. As soon as you see the phrase horizontal tangent, you should be thinking that the derivative needs to be equal to 0. If so, where? If not, show how you arrived at your conclusion. Well, I'm not talking about f prime because I don't have a function, I have a relation. I'm talking about dy dx. My dy dx that I found was y over 3y squared minus x. So I'm going to set dy dx equal to 0. Multiply both sides by your 3y squared minus x. And I get 0 is equal to y. So upon initial inspection, the answer is yes, horizontal tangent when y is equal to 0. However, if we actually are talking about a where, we're looking for an x value, right? So where is this going to happen? If I take that y value of 0 and I sub it back in to my original curve, I end up that 0 is equal to 2. Can 0 ever be equal to 2? No. So yes, there's a horizontal tangent when y equals 0. However, y cannot be 0 in our given curve. So there actually are no horizontal tangents on this curve. So again, when you see a horizontal tangent, derivative is 0. Then you got to make sure that you actually have a coordinate that makes the derivative equal to 0. The other thing just to be mindful of is that a lot of people talked about horizontal asymptotes, which is end behavior, and the limit at infinity. That is different than a horizontal tangent. A horizontal tangent touches your curve at one place and is horizontal. A horizontal asymptote means that your graph is approaching a given horizontal line by the time you're way out at infinity.